Hello and welcome to Turntide Technologies Motor Solution Overview. My name is Nick Nagel. I'm a Senior Director of Research and Development, and I'll be talking about our motors and motor controllers. But first, I'm going to turn it over to my colleague, Levi Thornton, to introduce our overall solution. Levi?
Thanks, Nick. Hey everyone, I'm Levi Thornton. I'm our lead product designer here at Turntide. And before Nick gives, our overview of the motor itself, I like to kind of set up the whole solution and help people understand what our various pieces of equipment do, how we get power out of our system by connecting it to the cloud and being very specific to the applications that the motor goes into. So I call this unwrapping the Turntide onion because there's a bunch of different layers, and much like ogres, onions, and Turntide also has a bunch of layers. So let me jump right into it. At the bottom, the core of the onion is the motor itself, right? These motors are central to everything we do. They take electrical energy in and make mechanical energy out. They are, they're where the motor of our motor system comes in, but without the next layer of the onion, they're really just kind of they're a hunk of steel and copper at the end of the day. So the next layer is the motor controller, and this is where the brains of the operation comes in. And before I get any further, let me call out, there are some SMC labels on the equipment that I'm showing you here. SMC is the prior name of our organization. We actually just went through an amazing rebrand to Turntide. Some of our assets still haven't been updated to Turntide, so you're seeing some SMC stuff here, but just know this is SMC equals Turntide. So the motor controller itself is the thing that controls the motor, hence the name, right? The motor controller is switching the current to the motor thousands of times per second to make sure that it is as efficient as it possibly can be. And it's got a bunch of smarts on board too. It connects to other equipment so that it can be controlled depending on the application that it's in. And it's also aggregating and collating data so it can get up to the cloud. And how it gets up to the cloud is through our supervisor. This is a pretty standard IoT gateway device, but it also has a bunch of inputs and outputs. You can see those little green terminals on either side of the device there. And that allows us to integrate sensor information from the equipment that we install in, so the things that we, not only to control the motor better, but also to understand the environment that the motor is running in when we're monitoring it from the cloud. And lastly, there is the cloud itself. This is where we see all that data. This is data from the sensors, data about the motor operation, about its efficiency and its reliability, and its alerts when things are going out of range, when it's not performing as it should. And this allows us to share this information with our customers. It allows us to bring it back into our engineering processes and tune the motor. And all around, it makes it much easier to service our equipment. So that's a high-level overview, but I can go into every device in a little more detail. What makes the motor and motor controller so special is their efficiency, right? A motor's efficiency is how much power you're getting out of it for the electricity that you're putting in. More efficiency means less energy use, which means dollars in your pocket. But not only is the motor more efficient at its rated power, at its rated load, what really sets it apart is its efficiency across all speed ranges. And so the switch reluctance motor technology is a variable speed motor, which means that you can run it not just at 1800 RPM at its top speed, but you can bring it down to 200 RPM, and it's still going to be very efficient. That's in comparison to other motors that we compete with that are going to drop off very steeply in their efficiency at those lower speeds. And Nick will definitely go into that in much greater and more astute detail in his presentation. So I'll leave my overview there. The other thing that I wanted to touch on is the simple design, and I called it a hunk of steel and copper. And that really, at the end of the day, that is the great part about the motor, is that its simple design makes it much easier to manufacture, much cheaper to manufacture, and with less complicated parts inside it, it's more reliable too. So in addition to being more efficient, it's also saving you money by just being hardier. The motor controller has a bunch of built-in inputs and outputs on it, as well as customizable controls. And this is a really important part of our solution as a whole, which is that motors don't just run as motors. Motors run inside equipment, right? So motors run, they can run fans, they can run pumps. The thing that the motor is installed in will determine how the motor needs to behave. And so by having this extra I/O on the device, and by allowing us to write programs specific to the application that the motor's installed in, we can make sure that you're using that full speed range and the variable speed nature of the motor to the best of that application's ability. So step up from that, like I said, we have the supervisor. And so the supervisor can do that kind of application specific control for a fleet of motors, right? It can do 10 motors wired directly to the device, or it can do 25 wirelessly if they're really spread out. We're actually boosting that number right now to over 25. Stay tuned for that. And it can also, using all of those wired terminals on the sides, it can connect to sensors and actuators. So you can get temperature and humidity and pressure values. You can get current values from other equipment nearby to know if things are online. And all of that can make you run the motor more effectively. For instance, turning down the motor when the air doesn't need to be super cool. And it's also our IoT gateway. So this is the device that helps us shepherd all of our data up to the cloud, not just the motor data, but also all of that extra data plugged into both the motor controller and the supervisor. And you have a little screenshot here, but we'll go into a little more detail on the next slide. This is where we get our customizable control routines, like I was mentioning before, that help us tune our motor's behavior to the applications in which it's installed. When it's running on the supervisor, not only can it control one motor as intelligently as possible, but because it's actually controlling this fleet of motors, it can do more intelligent things about balancing the load across multiple motors, or turning on some motors and not others to make sure that they're getting equal runtime, right? So this can synchronize your work across multiple different systems. So going into a little more depth, I like to give people the inside look of how our solutions engineers actually write these programs, and it's a visual programming language at the end of the day, right? You read it left to right. You're reading sensor values on the left, or values from network devices. You're running some comparisons, like greater than or equal to a specific temperature. And then at the very end, you're saying, look, turn on a motor group, set the speed for this motor group. And so we put a lot of effort into these programs to make sure that they're running the motor as efficiently and safely as possible. And one thing I want to call out here is, we have this one sensor value, and I want you to put it in your mind, store it for the next slide here, which is just that we have the ability to define kind of custom points in these variables so that we can send them up to the cloud and visualize them and compare them to the operation of a motor to know how they correlate, how they might impact the performance of the motor, or if we see a failure in either the motor or the equipment that it's installed in, how are these environmental points impacting those failures? So lastly, of course, above the supervisor on that IoT pipeline, we have the cloud, right? This is one screenshot of our cloud system. And at the end of the day, the cloud is monitoring every single Turntide motor that is connected to the internet. So they all establish their connection to the cloud, and they send their data up so that it can be monitored. Like I mentioned at the beginning, this is where we can configure alerts and email and SMS alerts for issues that could be detected either in the motor's firmware, if we really know if it's something really tightly coupled with the motor, or it could be specific to the application. For instance, if the air is too hot, even though we think that we're conditioning that air to be cold. This is where we can share dashboard access with our customers so that they can see their own equipment and know that the motor is running as promised. And then of course, we can correlate the data of our motor with all those other points in single dashboards and show them on the same chart and share those charts so people can better understand how those pieces of equipment are working. And like I said, to remember that point, that indoor temperature. So here it is, right? We configured it in that program that's running on the device on site. And then just like that, it's available on our dashboards, trended over time to be compared against our motor data. So a high level idea of how these things all get wired up when they're on site. This is kind of a Christmas tree scenario here. At the very bottom, the very, very edge of our stack, you have the motors themselves, and they're plugged in one-to-one with a motor controller, right? So every motor has one motor controller, every motor controller has one motor, and no other device can run, or no other controller like a VFD can run an SMC motor controller or SMC motor, and the SMC motor controller, Turntide motor controller, can only control our motors. The other devices that we're showing here are like a thermostat or a duct temperature sensor, things that might go next to the motors in those pieces of equipment that can be feeding their data into those motor controllers to get aggregated into the system overall. Those can also be, plugged right into the supervisor. Here you see the thermostat going to the supervisor. Again, just aggregating and sending up to the cloud. So the supervisor is really the connectivity device. This is the one that's sending it to the cloud or to third-party systems over building protocols like BACnet. And then over here on the right, you can see the kind of data that's getting added into the system at every level. So from the motors, we're getting things like its speed, its torque, any faults that it's detecting, or anything that's plugged into the motor controller or wired into the motor controller, and any points that might be application specific. Similar at the supervisor level. And then once it gets up to the cloud, that's when we can do more advanced analysis, trending, an individual motor's performance to the performance of all motors we've ever fielded before, right? We can do things like, of course, understanding if it is connected to the cloud, but we can also understand, is this motor displaying the same values as the other ones in its family, to make sure that everything is consistent in the field. And everything that we get is available every minute, right? So every 60 seconds, we get a reading from the edge so that we always have the latest real-time understanding. So that gives a really good overview of kind of how the elements of our system come together. Nick is going to go into way more detail about the motors this level down here. But I also just want to fit in a plug for the Turntide Learning Center. It's right on our marketing site, but I like to make sure that people are aware of it because this is where you can get individual equipment level data sheets. You can get our case studies, things that you want to know about the equipment itself. Start here first. Oftentimes when I have a question myself, I think, oh, that's probably in the Learning Center, and it is. So props to our team for putting this together. It's a great resource and a good first step whenever you want to learn more about the Turntide devices. So let me hand it over to Professor Nagel to walk more into the motor itself. And let me stop sharing my screen here so you can, Nick. And just make sure that you call things Turntide and not SMC like I did, Nick. I think you're still on mute.
Great, thank you, Levi. Okay, can you see my screen? Perfect. Let me go into presentation mode here. Thank you, that was a great overview, and I'm gonna dig in a little bit more, as Levi said, into the motor and motor controller side of things. And I'll start with an overview of switch reluctance motors. Our motor solution is a patented form of switch reluctance motors, and we'll talk about that a little bit. But I wanted to give you an overview of this. And this is really going to be at a higher level. If you have specific questions, feel free to reach out to us and we'll do our best to address those. But one of the questions I get asked quite a bit is, well, how does the Turntide motor different from other motors? And I found this chart online, and this chart is a high-level overview of the different forms of motors. And the different forms of motors, and you can see there's a lot of different categories of motors. So even answering the question, how is it different, how is it similar, is a little bit challenging. But we can break these down into two main groups: DC, direct current machines, and AC, or alternating current machines. So we're gonna talk about ours specifically, but we'll also talk about the other competing motor technologies out there, so you get a good feel for how does this all fit in. One thing to point out, the ECM, the electronically commutated motor, which many of you will be familiar with, or commonly known as the brushless DC motor, although it's called a brushless DC motor, actually has alternating currents and fits into the AC family. Now, where does a turntide motor fit in? Well, it's a switch reluctance motor. So if we follow down AC motor, synchronous motor, it's reluctance motor, and finally we land here in a switch reluctance motor. So the turntide motor is a switch reluctance motor, and similar to, or the other form of reluctance motor that's you see out there, may have seen, is the synchronous reluctance motor. Now the switch reluctance motor has a switched field, which very, very efficiently attracts the rotor, creates torque, creates motion, and really works in an effective manner. A synchronous reluctance motor has a continuous rotating field, and very similar to induction motors, which also have a continuous rotating field, also have some issues associated with them. The windings are distributed, and that makes installation, manufacturing more difficult and more prone for long-term failure. So we'll get into that a little bit. But I did want to address the different types of motors out there. And really what we're finding in our solution is that this is really being the best option for an overall system solution. So in terms of price and performance and ruggedness, availability, this is really proving to be above any of the existing motor technology that's out there. Now, what is the predominant motor out there? The predominant motor out there, the biggest incumbent, largest use in HVAC and really most industrial applications, is the squirrel cage induction motor. So if we follow this path through AC induction, so these are asynchronous, three-phase, the most common motor out there, squirrel cage motor. Really developed in the late 1800s by Nikola Tesla, been around for over 130 years, and really the technology was fantastic going back a century ago, but you know, it's kind of developed as far as it can possibly get. Biggest competition out there in terms of industrial applications are these brushless DC motors, or in the sine wave. So sine wave permanent magnet motors are the surface mounted interior permanent magnet motors that you might see out there as viable solutions. And these are our biggest competition in terms of performance. These have comparable efficiencies to what our high pole switch reluctance motor has, but generally at a significantly higher cost. And they also suffer from having rare earth permanent magnets. Now you might think, well, there are motors out there without rare earth permanent magnets in there, and that's true, but the highest efficiency permanent magnet motors are all using rare earth permanent magnets, and these suffer from sourcing issues. I mean, in addition to all of the geopolitical sourcing problems you might have, just availability of this in the next decade is really projected to be quite an issue for the industry. So our switch reluctance motor doesn't have any of these, doesn't have that issue because it doesn't have any permanent magnets in it. So let's talk about magnetic force and how we produce force, or force at a radius for torque. Well, I'll give you a very, very simple analogy that maybe you've seen in a grade school or high school physics demonstration. If you wrap a coil of wire around a nail, a ferrous nail, and you hook a battery up to it, you close a switch and drive current through it, it creates a magnetic field which attracts another hunk of magnet. So makes a electromagnet out of it. And the takeaway out of this is simply passing current through a coil of wire around a magnetic steel creates a magnetic force. In a switch reluctance motor, we take advantage of that. We have this very simple structure shown here. So this is nothing more than an iron core on the rotor, iron core on the stator, and the stator pole has wire wrapped around it. When we energize that coil, when we pass current through it, we create a force shown in black here, and a portion of the force is radial and a portion of the force is tangential. And it's that tangential portion of the force that creates torque. The radial portion isn't. And it's this reluctance force that wants to align the rotor to the stator whenever we energize the stator. So let's talk about the HSRM, which is the high rotor pole switch reluctance motor, which is a technology that Turntide currently has patented. This motor, like all switch reluctance motors, and as Levi said, is really at its core just a hunk of magnetic steel and copper with a series of bearings on it. So very, very simple construction, as simple construction as you could possibly get. And if we blow that open and look on the inside, here the stator is exactly what we talked about going back to the first principles of your grade school physics or high school physics. We have the magnetic steel, which is the iron in the analogy I gave. We've got magnetic wire wrapped around that steel, just like we did here. It's done here. And you'll note that these are coils of wire that are wrapped around a bobbin. So they're actually wound externally and then simply placed over the pole. So very, very easy construction. Now, if you look at an induction motor or a synchronous reluctance motor or surface PM machine, any of these AC machines that have distributed windings, it actually distributed means the windings are in many, many different slots. And the windings have to be, the wire has to be pulled in this narrow opening in the stator teeth. And so not only is that a difficult, much more difficult operation, as you would imagine, than simply sliding a bobbin on a stator tooth, but these windings, these end windings here, end up getting mechanically formed. So they're mechanically compressed, oftentimes with a rubber mallet, just literally beaten into place to form them. So again, in terms of robustness, that's not the most robust way to make this. No, manufacturers have figured out the right amount of force to hammer these windings in without generally doing damage, but we avoid those considerations altogether. So the takeaway that I hope you see here is that this construction is much simpler, lower cost, and more reliable. We don't have any issues of potentially damaging during the manufacturing process, damaging the coils. So how does the high rotor pole switch reluctance motor work? Well, it works like any switch reluctance motor. We energize a coil, and I said that reluctance force is trying to align the rotor to the stator. So we energize a coil and we start to align the rotor pole to the stator pole. If I energize the next stator pole, I align another set and another set, and this goes round and round. And for those of you who like to be mathematically precise, the torque produced by any phase is the spatial derivative of the co-energy. And actually that's even an approximation that we won't get into, but that's really unnecessary. What's necessary in terms of understanding what's happening here is we're making an electromagnet and we're attracting this. And the important thing, and one of the things that the brains of this does, the motor controller does, is it energizes the different phases in a very specific timing sequence, because the timing is critical to extract the highest efficiency out of this motor. So I'm going to talk a little bit more about the motor system as a whole. And as Levi pointed out, it has to have a brains associated with it, has to have a motor controller. So many of you might be familiar if you work in the industrial world and you're used to dealing with induction motors and variable frequency drives. I want to kind of highlight some of the similarities and differences. So as I've said before, we've got to attract this in a specific sequence. We have a power electronics bridge which switches one of the phases in, and then switches the next phase in, and then finally switches the third phase in, and repeats this process, continuing the rotation of this rotor throughout this and continuing the motor operation. So the takeaways here are that these power devices, just like in any VFD or any other drive, act as switches to deliver current to the active windings in the system. So really, they're acting as the switch in this magnet nail example that I gave. So how does our drive compare to a VFD that you might be used to working with? If we look at the topology of it, it's very, very similar. It has power electronic devices, IGBTs for switches, power diodes for recirculating paths. And really, if you note closely, there's only two differences. One is where our diodes are located. So you simply move the diodes around. And the fact that we bring each wire to each phase. So we have 2 wires per phase as opposed to 1 wire per phase, which is hooked up. So we actually have 6 wires going out. And that's actually a big advantage for us. And it's a big advantage because it essentially eliminates, all but eliminates, the common mode voltages that create circulating currents that end up prematurely failing bearings in VFD driven motors. So this is one big advantage. Again, another item that really helps with the overall long-term reliability of the system. Essentially, though, it has the exact same reliability. Why? Because it has the same BOM, same IGBTs, same diodes, same materials that go into our motor controller that are already in a VFD. So we're going to have the same reliability, same cost, and unfortunately the same drawbacks associated with it. Anytime you install a drive that's got a diode bridge as a rectifier front end, you get more input harmonics, distortion, EMI. And if those are important considerations, we have solutions just like other manufacturers have filtering solutions to handle that. And we also provide the same benefit of variable speed operation. It's inherent. But in addition to that, we have some significant advantages over the similarities. And here's where we're different. First of all, we get better speed control. The speed doesn't drop with load. In an induction motor, unless you're adjusting that variable frequency and closing the speed loop with a speed sensor, you're going to get a drop in speed as the load increases. With ours, these are operated sensorlessly, no speed sensor, no additional motor sensor needed, and you automatically get precise speed control. And then as Levi mentioned, we have all of the I/O functionality, the streaming to the cloud. And this I/O functionality gives us a mini PLC programmable logic controller available at each application. So the takeaway from this is that the VFDs and SRMs are very, very similar. We're just moving some parts around, but we also provide some additional benefits associated with that. So how do our motors compare to other motors? One of the biggest questions, and probably one of the biggest questions that might be on your mind. So let's talk about it. Earlier, I talked about how the most pervasive motor out there is induction motors. Induction motors are asynchronous motors. So all other motor types that you'll really see in the industrial world are synchronous motors. Well, what's an asynchronous motor? What's an induction motor? Well, the asynchronous operation has to do with the squirrel cage nature of the induction motor. So if you imagine this rotating magnetic field that happens in a 3-phase induction motor, and you look at the bars of a squirrel cage rotor of an induction motor, asynchronous rotor is always turning at the same rate as the magnetic field. So asynchronous means there's slip. Slip is the difference in speed between this rotating field and the bars or the rotor itself. So I had a blue bar colored so you can see that magnetic field is actually zipping by it. Now that ends up causing additional losses. That slip causes additional losses. That slip actually induces, that's why it's an induction motor, induces voltages which create circulating currents which are necessary to produce torque. If you didn't have that slip, the motor would produce no torque and be useless. But because of that, you have these circulating currents which give you additional conduction losses. These additional conduction losses necessarily mean it's really not going to be as efficient. So when you compare the HSRM, our Turntide motor, with an induction motor, and you look at the performance curve from the series of speed torques. So what's shown is a speed torque curve of an induction motor, and this black line is the envelope of points that you can reach in the speed torque curve. If you look at the HSRM, the Turntide motor, we are always going to be more power dense than a standard induction motor you're going to see out there. We're going to be more torque dense. We're going to be able to deliver more capability in the same frame size. Or for a given power requirement, we can provide a smaller frame size. So that is a comparison of the Turntide motor solution with the standard induction motors driven out there with VFDs. And with VFDs, you have to have a variable frequency drive with an induction motor if you want to vary the speed. Otherwise, it's only going to run at one speed. But because of the asynchronous operation, it's always going to have higher losses, always required to operate with slip. And an important thing here is that you don't get precise speed control out of these. Now, synchronous motors, all other motors that we compare, including the switch reluctance motor, are synchronous motors. So these require motor controllers. But the benefit you get from that is you get higher efficiency and much more precise speed control. So from a high level, how do we compare to other types of motors that you'll see on the marketplace? As I said, the BLDC or ECM motors have some advantages. The permanent magnet solutions, anything with a permanent magnet, can be high efficiency, can be used in servo applications, generally good control. But the big Achilles heel is the permanent magnet materials associated with those and the sourcing issues that are a challenge now and only projected to get more and more of a challenge. As we talked about, induction motors, cheaper, more established, they've been around for well over a century, but their efficiency isn't as high and their speed load range just isn't as good. And finally, the synchronous reluctance motor, which is more similar to a switch reluctance motor in that there's only magnetic steel and copper in it, has some advantages there, but the disadvantages are that they're lower efficiency than what you'd see in the other types of synchronous reluctance motors, in the permanent magnet ones, or in what our motor is capable of offering. And it also has the same drawbacks of manufacturing processes associated with induction motors. So we come down to the high rotor pull switch reluctance motor, the Turntide technology motor. It has high efficiency over a very wide speed range. And one of the things that we do by tailoring our motors with our motor controllers, we don't use our motor controllers with any other motor. We don't use our motor with any other motor controller, as Levi said. So that gives us a significant advantage that we get to marry these and optimize these. And every motor and motor control solution has code that optimizes the efficiency over a much wider speed and torque range. So one of the big advantages of controlling both the motor controller and the motor in the system. And this really has been an advantage for us. What's the disadvantages? Well, switch reluctance motors are known for being noisy, for having high torque ripple, acoustically noisy. And really, we've made some great strides. We have a quiet series of motors that made significant reductions in this. And through materials, through magnetics design, and through software control, we are continuing to optimize and improve all of these disadvantages and get to parity with our competition. So as we drive down the disadvantages and highlight the advantages, this is really showing to be the best overall value. And it's done so in a short time. I mean, we've been around for under a decade, and in under a decade have made tremendous strides. And so as we continue in the future to make improvements to the motor designs, make improvements to the motor controls design, the firmware control of our motors, this gap will only widen between our competition and what we have to offer. And one other thing I'll point out, switch reluctance motor controls are difficult. They're complex. They're mathematically complex if you look into what's involved in the controls. And Turntide Technologies has invested a tremendous amount of time and effort really getting to understand and optimize this and continue to make significant improvements. So yes, it is complicated, but the other motor technologies that are out there, which are now considered to be simple in terms of motor controls, really are only simple because they've had decades of time and maturation of the control technologies associated with them. If you look at an induction motor, it's a series of differential equations that end up being nonlinear, cross-coupled, time-varying coefficients. When first looked at gaining tight control over this, it was a very daunting challenge. Through 4 decades of research, it's really become easy. So we expect that our technology is going to be deemed easy as well in the not too distant future. And other synchronous motors also carry a portion of reluctance torque in there that they have to account for. We're not only accounting for it, we're depending on it. So the takeaway here is that while other motor types are not considered complex from a control standpoint, they certainly were at one time. And our controls are proving to really simplify it. And from the end user operation, it really couldn't be more simple. It's plug and play solution for our customers. So in conclusion, our team is really, I really want to point out that, as I said, in less than a decade, we've really catapulted the technology that's been out there for decades, many decades, and in the induction case, well over a century. So we've been able to catch up in years versus the decades or century. We provide one of the highest efficiency motor designs out there, one of the most robust motor and motor controller solutions. And in addition to that, we provide data analytics. So it's not just the motor, not just the motor controller, but really an overall application solution. It's really proven to be the best motor drive technology for industrial applications, and we're looking to expand that continually as well. And when I say best, I really mean from a cost, performance, and functionality standpoint. There'll always be arguments over what is the best motor, and you can always make an argument and have a specific example for a very specific application. It will be motor type A or motor type B. But when you get into general applications, really what you're concerned about is, what are my not only purchasing costs, but what are my operating costs? What are my life costs associated with this? And ruggedness, reliability is just a key feature associated with that. And finally, we continue to work on developments and improve this. And as we do so, as the price of computational power comes down and allows us to do more and more, this gap between the existing motor technology out there and motor systems out there and what Turntide Technologies is able to produce is only going to widen. So future very, very bright. So with that, now I'll open it up to any questions you may have.
So feel free to unmute yourselves if you have questions. Maybe I'll get things started. Nick, you said the motor was just steel and copper, but it looked like there might have been a PCB on those models of the motor that you showed.
Oh,
Does that mean there are electronics on the motor itself?
Yeah, great question. So initially, yes, we had that there for various reasons. We had that there as a position sensor. We've completely eliminated that. So let me show. Sorry, here it is. Right back here is where we had a circuit board that's been completely eliminated. So no more is there a position sensor. This is all sensorless, which means you don't have to worry about the reliability of not only an additional sensor, but the wiring associated with it and the cost associated with additional wiring. So that's been eliminated completely. So really good question.
Awesome, thank you, Nick.
Oh, and I should say, to be fair, there's bearings in here like every motor, which allows the shaft to rotate, but those bearings are steel. So
Nick, could you comment on bearing life and protection with the switch reluctance motor?
Yeah, great question again, Greg, thanks. So as I said earlier, I alluded to it briefly in here, but because of our winding arrangement and our control configuration, we don't have these common mode voltages that set up currents that actually end up circulating through the bearings and end up pitting the bearing surface, the race in the bearing, which ultimately leads to premature failures. And that's actually been a very common issue associated with variable frequency drives and induction motors, or variable frequency drives and other synchronous motors, PM motors. So a common problem, and oftentimes in order to mitigate that, there's large bulky filters that have to be placed at the motor itself. So between the motor and the inverter, you might have some large bulky filter to try and really reduce the amount of currents flowing there, and really reduce that those bearing currents associated with those. And this isn't just, by the way, I should say, this isn't just theory. We've actually measured the shaft voltages. We've used very precise precision measurement equipment while running and compared bearing shaft voltages and shaft currents on an induction motor, VFD driven induction motor, and our motor system, and looked at those bearing currents. And it wasn't an order of magnitude different, it was several orders of magnitude different. So again, from a life standpoint, really, really significant not having to mitigate bearing currents. The other way that is common is you'll put a brush block assembly on the motor to bypass where those currents would flow so they don't flow through the bearings. Finally, one other thing I should say, these bearings are lubed for life, maintenance free. So this motor is assembled and good to run for life. No maintenance, no grease zerts on these. You know, that's part of the ruggedness and reliability associated with these motors. So great question.
So Nick, it also looks like that the coils are neatly wound, and the more coils you get in there would determine, I guess, more power and efficiency. Is there new technology that we have that could prove that we could get even more windings in there with the same amount of you know, bob and fit?
Yeah, Ron, great question. So it's one of the reasons that the HSRM is so efficient, is because of the amount of copper that we can put into the stator. So there are three main losses associated with motors. There's windage and friction losses that has to do with your bearings, the fan, things like that. But that's small in comparison. Two major losses are magnetic losses, which all motors have, and there are copper losses, again, which all motors have. And these copper losses, by increasing the copper, by reducing the resistance, you're able to significantly decrease the copper losses, the I²R losses, which improve that efficiency. So two things. We saw that they're wound on a bobbin. They're form wound in a configuration which allows the wire spacing to be as densely packed as possible. So that's one thing. So in a given area, we can get as much copper in there as possible by arrangement of the conductors. And the second thing is we have additional means of shaping the bobbin to allow even more cross-sectional area, to allow even more copper in there. So again, one of the key things about this, and in fact, one of the key things about the HSRM, the high rotor pulse switch reluctance motor, is that we can put so much copper in, we improve the efficiency. One of the reasons you might ask, well, what's the difference between an HSRM and a standard SRM? A standard SRM has less rotor poles than stator poles. All other, fielded switch reluctance motors out there had been less rotor poles than stator poles. The reason being is that the electrical frequency is proportional to the number of rotor poles. So if you have more rotor poles, you have higher electrical frequency. Higher electrical frequency means higher magnetic losses. What one of our founders, Piyush Desai, did as part of his PhD thesis was show that while I'm increasing the electrical frequency, which will drive my magnetic losses up, I can, at a faster rate, increase the copper area and at a faster rate decrease the copper losses so that my net gain is higher and I can get significantly higher efficiencies out of this motor arrangement than I can a conventional switch reluctance motor, and certainly over the other motor technology, induction motor technologies out there. So I guess in short, I think I like to talk too much here and answer too long, but in short, the answer is we can get more copper in, which means lower resistance, which means lower I²R losses, which means higher efficiency. Great question. Any others? Well, if there are no other questions, I think we'll end the session. Hopefully this has been informative. From Levi and myself, we want to say thank you for tuning in. Bye now.
Thanks, everyone.